We're live. Let's see if people can actually see and hear us. I'm gonna check Twitter and see what that looks like and if we are live.
Yeah,
I have no idea.
you see it going live, but it's the same as it was before.
All right, let's check Twitter real quick. YouTube, I mean. Anyone already there on YouTube?
Should we be able to see that here?
People, right? I mean, it says live on YouTube. Nice. All right. How do I? YouTube is way too complicated in the back. Yeah, we're live on YouTube.
Cool. Not gonna ask you to check Twitter.
That was way too easy.
Cool. So should I start already or wait a bit?
Yeah, let's wait. Give people a second to chime in. See if they start.
Well, then I guess do you want to check Twitter or see if it's?
Yeah, I'm opening Twitter on the side. I have no idea what this is going to look like.
Is it on the Twitter Signals account?
Yeah, it should be. Yeah, we are live on Twitter. I can see it here now.
Wow.
Here we go. That's the Twitter.
Wow, that's pretty cool. Yeah. I see myself and also see 0 viewers.
That's amazing. All right, I guess we're live on Twitter and YouTube. Perfect.
That's cool.
How's that working? There we go. I guess we can hide the screen for now since we're not doing anything.
Yeah.
And I have future pop on. Let me change that back to the lo-fi radio. All right.
Future pop.
I did not realize that was still on. I was trying.
Did it change automatically or was it?
No, I clicked it to change it. Your video gotten so much better all of a sudden. Hi, Nicholas.
Oh, look. Nicholas showed up.
Happy Friday. Friday 4 p.m. Friday afternoon. Is it afternoon for you? I wonder how many folks are going to tune in that were actually at KubeCon this week, which might be wild, because they still don't have enough.
Yeah.
I'm
assuming after a week of KubeCon, it's a lot to then 4 p.m. log in for a stream.
It's a rainy noon in Portugal. I mean, it looks sunny in Spain for you, Alfonso.
It's always sunny.
That's what I guessed for Portugal as well. But
we're actually having a drought right now. It's because in April, it's like the month where it rains the most. We had like flooding in our basement last year, but this year we haven't had a drop of rain.
Wow. Yeah, so different. Today in Berlin is like a super nice day for the first time. So I just had coffee without jacket on, just in the sweater for the first time in like 6 months, and it was almost too warm. I almost should have gotten my shirt out and thrown the sweater away. So
what's the temperature right now?
We just hit 20 degrees Celsius. Yeah, so not too bad. Way different than last week.
Yeah, last week was 9 and rainy.
Yeah. A little bit too loud, the music. All right. I'll turn that down. Let me know if that's better. Yeah, we have a new setup, so overall this is like going very well though.
Yeah.
We can turn down the music.
Seems to be very easy to use.
And we're live on YouTube and Twitter at the same time on both Polar Signals accounts.
Next step is Twitch.
Thank you, Nicholas. Perfect. Yeah, Twitch I thought of as well. You don't have an account there, but we could totally do that. And then, we could just because we can go to like Instagram and TikTok as well. But I doubt there's much of an audience for a tech company there. Okay, we are the group that didn't went to KubeCon. Yep, that's correct. Welcome to non-KubeCon attendees stream. everybody who attended KubeCon is like resting in the hotel room or just like leaving. I think they're like done at like 5, so like 1 more hour or something, and then they should be done.
I guess talks are still going on now, right?
Yeah, could be. KubeCon schedule. I don't know what last. I once had that, like my first KubeCon talk with Frederick like 5 years ago. That was like the last slot of KubeCon, and it was like 4 p.m. on the Friday. It went great, but yeah, as imagined, fewer people showed up at that time. But doing a first time talk at KubeCon, it wasn't too bad overall. To have that with a fewer attendees. Where's the Monday, Tuesday, Friday? It already shows Friday. Yeah, they're going to do interesting. There's still talks at 5 that start at 5. That's wild. But yeah, there are definitely talks that just started now, a bunch of them. Let's see, cross-plane, connecting, Kubernetes infra-sig, SIG network, what's new in the operator framework. Yeah, I mean, yeah, people can still attend KubeCon talks right now.
I also heard that it's in Paris next year.
That is correct. Yeah, it definitely is in Paris. So
cool.
It's pretty cool.
So, slowly moving back to Valencia. That's where I live, by the way.
Yeah, Berlin-Valencia connection here. Paris is right in the middle, I guess. So
yeah,
it should be good for the both of us.
Exactly.
Nicholas had FOMO this week, but it's over. Interestingly enough, I had very little FOMO, but might be just because I've attended so much over the last 5 years. But it was great seeing pictures of all the people that attended and the groups that met and stuff. So I'm going to skip through some recordings once they upload, probably. Anything in particular you had FOMO over, Nicholas? Anything you had FOMO over, Alfonso?
I don't know. I mean, I think maybe there was this future of eBPF talk that was interesting, and actually in general, like, and I think that was like a co-located event, right? I think in Valencia I also had that feeling because I only had like a general KubeCon ticket. Had the feeling that I kind of wanted to attend a co-located event, but the cost is definitely a deterrent.
Yeah, it was the observability day Nicholas also mentioned.
Yeah.
And apparently I didn't even realize the talks are already published.
Awesome.
That's pretty sweet. So
cool.
I guess you can leave the stream and go and watch that.
Can I leave the stream and go and watch that? I'm just kidding.
We'll just like watch YouTube videos together now. But yeah, there were a couple
this
of good
is a stream for YouTube videos.
I wonder like what the feedback is going to be for Observability Day, because they merged a couple of pre-day events into one, and that was called Observability now. So Observability Day now.
Was there a reduction in price as well, or something like that? I think it was like some talk, right?
There was like a different purchasing model basically. So I think the price stayed the same, but you could decide between 2 co-located events where you could go back and forth between one or the other, and you could go to Observability Day and then eBPF Day or something like that. But I think you had to decide which 2 you want to get or something. I mean, I don't know for sure because I didn't purchase a ticket, but that's the way I understood it. And then you could like go back and forth like to the talks that you were interested in, and you weren't just stuck in the one specific room that you bought. So I think that was a better approach. I don't know. Yeah, I'm overall curious how that went, and like also the Observability Day, how that went. I'm curious to hear folks' feedback overall. I know that like Frederick did a talk there that I think you mentioned, Alfonso, right? Was that the future of eBPF observability?
Yeah.
I know there was a KubeCon talk. Yeah, that was
a
pre-day. Yeah, there was one that Sumera proposed and Frederick did on
profiling
wire formats for profiling. Yeah, exactly. So that one happened, and then I know that like Lily Georgette was on the panel discussion for Observability Day. So that's definitely worth checking out as well, I think. Yep. And I'm sure there's plenty of other stuff. It's just the things I'm aware of, and I'm curious to dive into some of the other stuff there that happened on that Tuesday. Right.
Do you know how many people are watching?
That is a good question. So maybe I shouldn't have closed YouTube again.
Nicholas asks what we're using for the streamer. Yes, we're using Restream. Trying it out for the first time today.
Yeah.
Matthias set it up with our company branding and is using it pretty well.
Yeah, it definitely makes it easier. Like once you're like more than one person streaming, I think that it becomes a lot easier to set up. And like the previous couple of times we like had like a Google Meet, and then we were like screening, like recording that video at that window with OBS and then cutting the sides and everything. But this is almost like just joining a Google Meet on its own, right?
Yeah, I'm I guess a guest, and it was as easy as just clicking a link like Google Meet. And Matthias just moves me around and then shares my screen
exactly
when necessary.
That's awesome, Nicholas. Feel free to drop the link to your stream in the chat so people can watch it. I love Argo CD, so definitely curious on how that went. Let us know. All right. Should we get going? We're like 10 minutes in, so we can.
Yeah, it sounds good. I can get started, and then as more people join, review what we've been talking about. So, I guess first of all, I'll sort of explain a bit who I am. I'm an engineer at Polar Signals, along with Matthias, and I'm focused mostly on the database side of things. So, as most of you listening probably know, Polar Signals is a continuous profiling product that uses Parquet to collect profiles of your programs and then has to store them somewhere for like later visualization. So I'm focused on the database side of things and storing and visualizing. And my previous experience was also at a database company. I was at FrostDB for around 5 years, also working in Go. So basically, I've been working on databases in Go for my career. So we'll do a little bit of a dive into database performance, looking at some profiles today. And the database we use is FrostDB, so it's a columnar layout database written in Go that is also embeddable. It's fully written in Go. There's no dependencies on C++ or anything. And yeah, we use sort of a distributed deployment of FrostDB nodes to store our profiles. So yeah, I think basically ready to start sharing my screen and taking a look at some of our profiles in our production cluster.
Maybe you want to like quickly show where people can find the FrostDB on
yeah, of course. So Polar Signals FrostDB, basically. This is the repo in the Polar Signals organization that stores the FrostDB, which is completely open source. It's public. So I guess maybe I can also go a bit around like how it's structured. So as I said, it's a columnar database, right? That stores it's sort of meant to have an in-memory layer, which is you can think of like the active, most recent data. So as you write data to FrostDB, it keeps data in memory and then has an option so you can flush data to object store once you hit a certain size limit. And the data itself right now is written using the Apache Parquet format. So this is mostly used because of some good compression that we can get from Parquet. So we basically get some Parquet files sent from whoever's trying to run to this database, and we organize the data according to using a B tree structure. Basically, that's our index structure. and we only support primary indexes for now. So we have, when you're running this database, you can specify the ordering of columns, which is the primary index in a database, and we only support like one ordering right now. So we basically store data in a B-tree format, so we can very easily, traverse using ordering guarantees and find the data we're looking for when we read data. And in our case, we're looking at profiles. So some of these columns of the data we're working with are like types. So CPU profiles, then the timestamp, because each row you can think of as a profiling sample. So the timestamp at which the sample is taken, and then some extra data like labels. So where was this sample actually retrieved from? And that's actually an interesting thing that this database does, is that you don't really know your labels as a user up front. So you can't really define all the columns in your schema when you start up your database for the first time. So FrostDB supports using something called type-wide columns. So you can define a column which is called labels, and then that column sort of has sub-columns. You can just add more columns to that column. Saying column a lot of times, but you basically can define a nested structure of columns as you have more labels that you're starting a profile. So FrostDB sort of like supports that use case, which is use a lot of observability, because you want to define where all your data is coming from to be able to slice and dice as you please. So I think that's basically the general explanation of FrostDB. And as you can see, also we use Apache Arrow at query time. So because Parquet is not a format you can easily execute queries on, it's good for compression, but not for manipulation. So we need to convert into Arrow, materialize all that data, and then start working on Arrow records once we get requests for aggregations or whatever based on those profiling samples. So Matthias, do you think I'm missing anything? Would you want to add anything here?
Not really. I think it's like the dynamic columns with the labels, I think, is like probably best explained for people at least that know Prometheus, with like the labels that Prometheus also has, that are like super dynamic, and they come and go as Go workloads come and go. So even just the deployment of something like creates totally new label values, sometimes even new label names and values altogether. And I think like as you said, it's super dynamic with that dynamic column, as the name suggests, but like it's actually at runtime, right? So you don't even know what columns you'll have up front, and FrostDB is built with that in mind, and can handle all of these like dynamic columns that are going to show up. So I think just underlining what you already said, or like kind of like rephrasing, but I think overall really
sounds good. And if there are any questions about the database, just drop them in the chat and we'd be happy to answer them.
For sure.
Okay, so moving on to the meat of the stream. Yes, this is the product that we sort of show it when you log into Polish Signals. Have we used the cloud product before on the streams, or is it mostly Parka?
Sorry, I was reading chat. What's that?
I was wondering if we'd used this cloud product before, or we only showed the open source Parka version.
No, we have used Polish Signals Cloud on the streams, basically exclusively. But yeah, you can think of it as like a multi-tenant Parka that is also horizontally scalable. But overall, if you know Parka, it should be super familiar.
Yeah, cool. So basically, we want to look at the last 15 minutes of profiles, and we're seeing some very high CPU usage in a lot of areas. But I think like one thing that jumped out at me when thinking of things to do with the stream was that, if you look at the labels that pop up as I hover over these lines that are taking up the most CPU usage, because I'm looking specifically at CPU samples collected by our eBPF Parquet agent, right? So the lines kind of represent the values, the CPU usage at that timestamp. So as we can see, like one of the most things that's taking up the most CPU usage relatively is our storage node. So this is, as I said before, a distributed deployment of FrostDB nodes. So if we would drill down, we put something like container storage, and this is filtering by label that we talked about before. So as I was hovering over that series, you saw like a bunch of data show up, which was anything from like what the container name is to maybe even like what Linux kernel version we were profiling at that point. So this is basically a lot of the high CPU usage that's going on in our application. And our goal here today is going to be to reduce the CPU usage. So mostly when I'm looking like icicle graphs, I think what's the thing that's taking up the highest percentage of CPU over this time. So like this is a merged profile. And that's like really the beauty of continuous profiling, is that each of these data points you can think of as one profile taken from the application, but you can get some way more interesting data once you like start to merge, for example, CPU usage over time, and see where the real hotspots were, rather than just getting a profile at one specific point and maybe missing some interesting data. So what this view is giving us is aggregated CPU usage, not only over time, but also over each of these time series. So each of these time series, they're very similar in that they're running the same container. But as I said, this is a distributed deployment. So each container is a different, it's actually a different pod, right? So that it's got a different pod IP. If you can see, the thing is that there are so many labels, it's a bit hard to highlight them because I can't move my mouse, otherwise it disappear. But at the bottom, you see like, pod IP, pod name, and PID, which is the process ID on the actual node that's running this container. So let's, I guess, dive a bit deeper into what is actually going on. And these are different Go routines, basically. It's fully Go. So I don't know if some people haven't worked with Go. Go routines are basically threads. So these are all spawned from the main Go exit thread, which is the thread you're running when you run a Go program. And I'm gonna maybe skip over like these little ones because they probably don't matter that much. But in general, we see some memory, some CPU usage in table block persist, which we'll get into these a bit deeper. Compactor pool. Obviously, there's serve streams that if we go down, we see it's inserting into a table basically. And I think this is probably going to be what we want to improve today. And then this is really interesting because this is a GC. So Go routines relate to GC and Go, because Go is a garbage collected language, and the garbage collector runs periodically to kind of mark objects and then also clean them up to reclaim some memory and give them back to the operating system. And I think that this seems like it's a background mark worker. I'm going to just zoom in a bit here. Background mark worker, which is probably, it looks like it's scanning objects and finding objects. So the interesting thing here is that like this Go routine is taking up a non-zero amount of CPU time, so around like 14% of total CPU time spent marking objects. I think that
non-zero is amazing when it's like 20,000 samples that we've seen and like 13% of
of
CPU time.
Yes, yeah. And so I think like I would probably like intuitively say that what's happening here is that we're probably allocating a lot of maybe smaller objects. So there's a lot of marking going on, because it seems like the actual garbage collection, which should be maybe around here, GC enable sweep. I think this is the Go routine. Again, I might be like making stuff up as I go. I'm just saying like what I think is going on, but it seems like this stuff is actually what frees memory back to the operating system. But it's kind of interesting to see these like runtime Go routines. So we see that there's a lot of time spent in GC, which definitely affects performance, right? Because when this runs, that's like CPU time that your application can't use, and also it really affects stuff like tail latencies. So if you ever have like a Go program and you see like tail latencies are very high, or just all over the place, most likely your it's the GC that's messing with your application Go routines. Well, that's interesting. I think that's just like a data point, because we can't improve anything here because these are runtime Go routines, but we can change our application maybe to do less of these allocations to improve time. But let's leave this aside for now and go back to the start, which we call this persist Go routine. And as I was talking about like FrostDB at the beginning, I said that it has like an in-memory data, like you're writing to these nodes. You collect by default around like 500 megabytes, and then you take all that data and you put it in object storage for querying later. Because this allows like block rotations, and obviously like at some point you have too much data to hold in memory, and you want to figure out some way to persist it, and object storage is a pretty good way to do that. So maybe going a bit what the persist call actually does, we see that there's a B-tree ascend call here. So as I said, the data is organized in a B-tree structure, and what we're doing here is basically going through every single node, and then serializing each node. And as I was saying, each node has basically got a bunch of Parquet files that represents the data that is stored in that node, and each Parquet file is put into a node depending on the actual data that is in the sorting columns that we define a primary index by. So we see that there's some serialization going on, row writing, and then and the interesting thing is that each of these nodes, you see that it's sort of like a recursive call, because at each level we have like a bit of the serialize function here. Then the next recursive layer we got serialize again, and so that's like the time spent in serialize at each layer of recursion. And at some point it's like also uploaded to object storage. But it seems like a big CPU usage here is actually serializing the table block to be able to just send those bytes over to object storage.
It's interesting that you can kind of like see what the most common amount of recursiveness, I don't know if that's a word, but like how often do we go recursively into the iterate function, right? And you can see that it looks like it's roughly like called 5 times for the most part until we write the actual column. So that's kind of interesting to me. I mean, we have like yesterday we discussed that kind of recursive functions are really nicely shown in like call graphs as well. But I just like had this like thought where, oh yeah, this is actually cool to see like what's the most common amount of recursive calls we have. Just the width of the.
That's true. And it's kind of interesting to think about it as well, because it shows you the depth of the tree. Mm-hmm. Not necessarily the number of nodes, but
the height, right?
The height. I haven't talked about trees. But yeah. And so the next Go routine is taking up a good amount of time. 10% is the compaction Go routine, which as we see is another iteration of the B tree structure. And the reason we're doing all this compaction is because we get a bunch of data from the writers that then all this data that they're writing might have different values for the columns that we're ordering data in the B tree by. So what we have to do is like figure out where in the B tree it goes and then put it in that node. And that's like introduces a lot of fragmentation, right? Because you have one write, you distribute those rows in the B tree according to like where they fit. And then you're basically accumulating single rows in the B tree. And as we saw, like they're stored basically in Parquet format. So each small amount of data is its own Parquet file. And the good thing about Parquet is that we get good compression. And the more files you have, the less you can take advantage of compression, because the less data there is in that file, and compression is defined at the file level. So this compaction pool basically improves our memory usage by compacting all these fragmented files into one to be able to take advantage of compression and reduce the active memory size. But again, this is not something I think we can, I mean, there's definitely probably some low-hanging fruit here, but as we saw, insert is probably the thing we should focus on. But compaction seems to be doing what it's supposed to do. So compacting level 0 to level 1, we sort of have an idea of leveled compaction in the B tree nodes. And then we go into a third-party library, Parquet Go, which is our open source Parquet library that we use.
Which is amazing. Shout out to the folks who mostly wrote it. It's really good.
Parquet Go maintainers.
Yeah, it's a really, really good library overall. Super well done.
So this thing, the inserts, are taking up 68% of CPU time, which is a lot.
Let's tackle that one.
Worth looking at. Yeah, definitely. So I'll zoom in again so we can start to see how an insert is broken down in terms of CPU time. So this split rows by granule, and by the way, I think most of the people on the stream probably know how to read Haskell graphs. That there's also a nice blog post that Kamal, one of the other engineers on Twitter Signals, wrote recently that you can check out if you want to learn more. But basically, just in case there are people that don't know how to read Haskell graphs, this corresponds to a function call. So when we have like one level insert calling it like and there's another level below, these are basically the functions that are called in the parent function, if that makes sense. And then the size of each rectangle is the amount of relative CPU time that child function is taking in its parent. So when I go down the stack, I'm basically looking at a call stack going down, like what did this function call? What did this function call? So here, insert, we can see they're called two functions. We see split rows by granule, and then is sorted. So sorted by split rows by granule, this is kind of representative of what I was talking about before, that clients write a bunch of rows, and we need to figure out where those rows fit in the B tree. So split rows by granule splits the rows and assigns it to a B tree node, which is the same. Like we basically use the term granules to refer to a B tree node. So this is basically what it does. And again, we see like a recursive iteration over that B tree to find exactly what node it belongs to, and then insert the row there. And on the other side, we have an is sorted function. And this is actually something I heard relatively recently. And as it says, it basically just checks that data is sorted. And this is because we can take advantage of a couple of nice properties if the data that is inserted into into our database is sorted. And if it is not sorted, it makes life very difficult. And actually, we were assuming that rows were sorted when in fact they were not. And this was leading to a bunch of correctness issues, which made us add this check-in. So like the first thing I can think of in terms of CPU usage is that this is sorted check is probably not necessary in applications where we've already fixed any kind of issues where your clients are writing unsorted data. It's probably good to have like in debug builds and stuff like that, but if it's taking like 18% of CPU time, that's a lot. So that's probably one thing I can think of we could probably change to improve CPU usage. But let's see, we've got to see also like what is using all the CPU, because the assorted call itself calls other functions that end up taking the CPU usage. So if we go down a bit, here we see, well, let's go into here. We see that, interesting. So here we see that we're comparing the rows, right? Checking for the sorted property we're looking for. And a lot of the CPU usage here is in new schema. Okay, so where a lot of CPU usage is actually creating a new schema for comparison. And maybe another interesting thing that I saw before diving into this part is that probably if we're looking at the B tree traversal, we also see that a lot of CPU usage, let's just zoom into this for a second. We see that a lot of CPU usage is also the comparison, basically all of it, right? Comparison again here, which we said was like a different recursion level, and comparison. So if we look at these comparisons, only this recursion level is already taking 20% of CPU time, plus whatever this one's taking, plus whatever this one's taking.
Yeah, that's like 30%, I think. I just quickly added up. Yeah, 20 and 6 and 4. So yeah, plus, 30%.
Plus this one, which is another 6%, 36. Yeah. And then also what we saw in the is sorted, right? Mm-hmm. Which was down here, which is also a comparison, which is 18%. Yeah. So this kind of gives me the idea that if we were to focus on this like schema comparison code, we'd probably improve things quite a lot. So does this make sense so far? Like how I got to here. I also don't know if there's anybody else that joined the stream. So a quick recap is that we're looking at our cloud product, which collects profiles and stores them in our database. And in this database is called FrostDB, which is open source at GitHub Polar Signals FrostDB. And we are analyzing here a very high CPU usage in our cluster that is mostly taken up by insertions. And right now we're seeing that a big part of what's taking so much CPU time are these insertions, which you can see that in the cumulative percentage. It's like nearly 70% of all CPU time over the last 15 minutes. We see that a lot of that is actually because of schema of comparisons between rows to see where we insert them into the B tree.
Yeah, I think just like to add to what you said again, it's not only the cloud product, right? Like we are looking at FrostDB itself, and whatever we do is also going to benefit Parker. So it was just the easiest to kind of just go about it and see what we have in the cloud product. But the underlying FrostDB is exactly the same, right? So like it'll also show up for all Parker installations out there, like, or even I don't know if anyone else is using FrostDB for other things than Parker already, it will also show up there. But yeah, maybe we can talk about just like the high level ideas of what the schema compare is doing next.
Yeah,
before diving into how to improve it, but just understanding what it does, right?
Yeah. So the schema comparison is basically doing, I think, two big things, like these extract values and merge down icons we can probably ignore for now, but this comparator call seems to be doing what we expect to be happening, right? Which is the actual comparison. Compare rows for each column, compare each value, basically, is what it's saying. And then on the other side, we see that a big part of the comparison is calling new schema, which it's a bit surprising because when you're comparing rows, you sort of like are inserting into a table that already has a defined schema, and if you're inserting rows into a table, you should have already checked that the rows that you're inserting like match the schema, and so you can just use a single schema. So that's what you would intuitively think, but again, FrostDB has got the idea of these dynamic columns, which are basically the labels or using the store profiles, and that kind of means that we need to create like two rows that are in the same table aren't necessarily like inserted using the same schema, because for example, each row represents a profiling sample, so your eBPF agent collected from a running program, and each row could correspond to different label sets, so like a different program that's running. So you could have, for example, one program that was like CockroachDB, and all the labels you have associated with cockroach are just that it's called cockroach. But then you might have another program somewhere else where it has a label but just about the Linux version of the machine it's running on. So you would insert these two samples into the same table, but they have, like, if you're talking about the concrete schemas that these rows have, they differ. And the problem is here that you want to compare rows like that, because you want to basically see like what label sets you have, and how do you compare like three distinct label sets. And the answer to that is that you kind of have to merge them together and then materialize some null values in the columns that the rows don't have. So for example, in our example, like the cockroach process, we would add a Linux kernel version to that row, but then set that to null, right? So it would be, we would sort of solve that problem by making sure that all the rows have the set of all labels that we ever know about, so to make it comparable. And but it seems like we definitely have something to look at here.
Mm-hmm.
And in terms of like maybe making it a bit cheaper to have these types of schemas for comparisons. And then this comparison is doing what it's supposed to do. But one very weird thing that I saw is that if we drill into here, we're seeing that for each leaf column, so for each basic value of the row, we're calling path, which here in Parquet, this path is basically equivalent to a column name. And the crazy thing is that we are actually allocating to get the column name, which is completely surprising. And actually, I'm seeing now
it should just be a string or something we already have, right?
Exactly. And we're seeing that, yeah. So this should just be a string,
mm-hmm.
and this ascending should also not be allocating. So because we're spending all this time basically just searching for a column in a row, which is the main CPU usage in like comparisons should be like the actual comparison, not searching for the value that you want to compare. So I would say, because it seems like we can take a look at the schema creation, but I think that probably the simplest thing to improve is these path polls, and take a look at the code and see what we can do there.
That sounds really good to me. Yeah, I think that
I'm
makes
gonna
sense.
pause there. Do you want to? Are there any questions or?
No, chat is really quiet. But I think we're actually doing quite well on Twitter. I think people are stopping by on Twitter or like watching on Twitter. But it seems like very few people now go over to YouTube, whereas like first and foremost, like last times we had people come over to Twitter, to YouTube. But I guess that's the magic of streaming to Twitter right away, right?
Yeah.
But yeah, overall, if you want to like write something in chat and you're like on Twitter, feel free to also head over to the YouTube channel. We have have a chat there so you can ask questions, but I think we can just continue as there are no questions.
Is there a chat on Twitter?
No, I don't think there is. That's why it's rather quiet. Yeah.
Cool.
Exactly. If
But
people are hanging out there.
So let's look at these path calls. Starting by, because dynamic sorting column seems to be called a lot more, so okay. This is basically the path call that we're seeing show up here. And we're seeing that's allocating, and so we see that this path is basically just returning a string slice, because it's kind of like a file system path, right? You have like different components of that path. It's the same idea for these Parquet columns. Although we have a very flat schema, so as you can see, our path is not very complicated. It basically just returns a slice of the column name, which, as you can see, is like set on the creation of that column. Actually, you can't see that. Let's see. Dynamic sorting column is made above. But yeah, you can see basically we create a column, and then we set the full name to the column name plus a dynamic column name. So this is, for example, we had a labels dynamic column, and for example, Linux kernel version would be like, this would be labels dot and then kernel version. So dynamic column name is the like concrete label that we're adding. So obviously, like, it seems like a pretty simple change, right? Because we'd just be doing something like setting something like the full path. Actually, maybe let's call that full name, which we'd set full name to, but then maybe we'd add like a path, which is a string slice of the full name, which should basically give us the same behavior as this path call. Because what we're doing here, calling column name, we're calling like a public method, but we're just returning the variable, the field, sorry. So if we change that to din.path, okay. So I like to test stuff with like micro benchmarks for us to see like what change we have. It also gives you probably the best numbers because there's less noise. So let's run a quick benchmark, because I don't think we have a benchmark for this stuff already, but let's see, what was it? Make dynamic sorting column. And with a name, so test, remove that. And then the second parameter was the actual sorting column. So this is basically this like annotating the column with a sort order that you wanted to have. So it's saying, like, for example, if you insert data into this column, make sure that it's like in ascending sort order or descending. So
just to let you know, like right now, I think we're like on top of the screen there. Yeah, exactly. That's
okay.
Way better. Yeah, perfect.
As long as Golang doesn't delete the new lines.
It does.
But
that works.
That works. Okay. So let's call that sort. And this is our column. There you go, tab 9 helping me out in getting the path. I really want to try GitHub Copilot, but I paid for like a year of tab 9, so I'm stuck.
Okay, makes sense.
Tab 9 for a year. Okay, so let's run this benchmark. Let's see, benchmark. I think this is actually in the dim Parquet package, right?
Yep. Yeah, it says on the very bottom.
Oh yeah.
Dim Parquet is correct.
Dim Parquet, run benchmark path. And since we're also looking for memory allocations, I'll run this with benchmem. Let's say account
5 or something, 10.
I'll put 10 and verbose. Let's see. So, well, actually, let's first run this on the main branch and call this bench main. Okay, so it looks like it didn't find it.
Yeah, because you probably have you stashed your changes?
Oh, that's true. Yeah, so I need
The benchmark's gone.
I need to unstash them.
You can only stash the schema go.
Yeah. I had this already.
It's annoying. That happens to me every now and then as well.
So now I can stash them and run the benchmark.
There we go. I wonder if we're gonna see you lag a bit more, but so far everything's good. I think like we had that on the stream where I think Frederick was running something, and then you could noticeably, you could definitely notice that he was running the benchmark, but this was totally fine. I guess the benchmark is light enough.
Yeah, maybe it's also because I got just got the new M2. Let's see what bench path then. So I pop my changes here. So I guess we can just run the benchmark. Okay, so this is pretty cool. Obviously, like we see the allocations like drop down because this is talking about the allocations per op, where before we were returning like a string slice from that method, which I think like the explanation is that string slice, like the compiler doesn't can't statically determine if it escapes, if it doesn't escape to the heap, so it kind of like allocates it on the heap and results in allocation. Like if we store that as a field, we allocate it once when we create the column, but then on each subsequent call to path, we don't allocate at all. And as we see, there's like a pretty good improvement, and we can get some more numbers using benchstat, which is, I don't know if people know, but it's like a nice performance tool that comes with like Golang xperf, I think.
Yeah, we definitely have used it on the stream before.
Okay.
I think that was like the main part of when Frederick and I did a stream a couple of weeks back. So yeah.
Yeah. So we see like an 80% improvement in that specific micro benchmark, which is pretty cool. So that seems like a nice improvement for this
already. Yeah.
Yeah.
Just by not putting that into string slice.
A very simple change, and that's really like what, like three a bit more than 3% of CPU time saved over 50 minutes. So it's like one of these things you're like, oh wow, this is like so simple, but makes such a big difference. And I think we could probably do the same thing. I don't know, like ascending path seems to happen the same thing seems to happen, right? So yeah, so we create a slice there, and return the ascending. The thing is that we don't have anywhere to store this path right now, and I'm not sure if would it work to just like make this a struct. I don't know. I haven't really.
Yeah, interesting idea.
The thing is that
where it's coming from.
We'd probably need to change like all call sites to change how we use ascending. But,
right, because it needs to like add creation time, put these fields in, right? Yeah.
Yeah. This will probably break a lot of things. Let's see.
Might be out of scope for the stream. Yeah, let's see the.
Well, actually, maybe ascending is like as we call it.
Not too bad, yeah.
Okay, we can try it. If it takes a long time. Okay.
Time box it until 5.
Yeah.
Yeah, 5 minutes.
5 minutes.
No,
okay. Good. So we change this to name. Actually, no. This should be path. That's what we're trying to improve. And this is already a string, so we don't need to cast it.
Yeah, I wonder if we can do something about the sprintf there. I don't know, is like the sprintf thing, is it like always slower than just concatenating strings, right? We could just like...
Yeah, it is, yeah.
So
we could just concatenate. The thing is that this string is probably not used much.
Yeah, fair enough. But that sometimes is an easy win.
Yeah.
To just do that. And you have like a curly brace too much, yeah.
Okay. So then this is really, I think, what we should change. So we return ascending with name set to column, and then path set to this. Well, I guess we could abstract that. I don't know. In interest of time,
yeah, some constructor. Yeah, I think it's somewhat simple enough.
So, I guess so. That should work. I mean, I don't think it's worth writing another benchmark for this. Like, we've already seen improvements. It's like 80%. The important thing is that it compiles. Our database compiles, so that's probably like another 80% improvement on 1%. So 0.8% improvement plus like 3 and a bit. We could say call this like maybe 4% improvement on the total time, just with a simple change. So that's good. But let's move on to the bigger things, which was the schema.
Yes, it's going to be interesting.
Which is, I think, going to be a more complicated change, but doable. So let's go back to compare. This is what we just improved. The new object, the allocations here in paths, which, by the way, we saw like there was a bunch of like GC mark time in the general view. So I think that probably like these allocation reductions will probably help because they kind of like follow the profile of what I think is causing that GC usage, like a bunch of really small allocations, which are these like single element string slices every time we try to find a column to compare with. So you can think of like, you know, all of these inserts happening, and every single insert for every single like column in that row, we're trying to do this find logic, which is, you know, taking a bunch of time. And also, I guess, like find, you know, you would think like, why isn't that like a constant time operation? And I'm not really sure, but there's like right now in Parquet it's implemented as like a linear search over the values. I think because you don't have like a concrete schema of the values, maybe. I'm not actually quite sure. Oh no, so I think what's going on is that we're creating this new schema using a comparator. So I think that maybe probably every time we start comparing a row using this schema, we need to figure out like what column indexes we refer to.
Mm-hmm. Yeah.
Oh no. What it is that when you pass a row to this comparator, like that row is seen the first time ever in its comparison function. And I don't think Parquet like defines that the row values need to map one-to-one to the column names in the schema. So each time you have this comparator, you need to figure out like the mapping between the schema column name and the row value, if that makes sense. Which I'm not exactly sure like why that is, but that's like why you need like a linear search, basically.
Wow, interesting. Okay, that seems rather complicated.
Yeah, I'm sure they're like, because Parquet, you know, the problem is that like with Parquet, it's like a very like general use library, like a library that is used in like many different ways. So you support a bunch of use cases, and I'm sure that like it doesn't make sense to us maybe, but I'm sure there are like some use cases that that probably need to be taken into account when designing these Parquet comparisons that that this aims to support. So I don't know. That's also maybe something to follow up on. That if we make column searching cheap, maybe it doesn't matter as much, because as we saw, like the biggest part was was returning the name of the column. But yeah. So talking about schemas, the other big thing that we saw that used up a lot of CPU time was this new schema call, which means that we're creating like a new schema on every single row comparison. And as we saw, like this was kind of necessary because we could be comparing rows with different concrete schemas, because we support adding dynamic columns to profiles. For example, labels that describe like where this profile is collected. So maybe let's take a look at that code and see what we can improve. I'm gonna hide this a bit, but we got like a nice insert benchmark that we can then run to see like the general improvements that all this stuff can help us with. But
okay, that's good. Maybe let's let's look at the thing first, but then let's run the benchmark this time before we start changing things, right? So we don't have to like stash and go back and forth, and we know some numbers up front. Yeah.
Do you want me to run it now?
No, let's look at the code first, but just reading it before like writing anything, or we can just, whatever way you like.
Okay.
I'm just trying to
no problem.
Avoid confusion going back and forth too much. And by the way, Nicholas, thanks for the comment. I guess Alfonso has a really good eye on where to look for performance improvements at this point. Reading flame graphs as a job. I guess.
Exactly.
Yeah.
This is what I'm paid to do.
Not only like reading flame graphs, right? But
not only
out where to.
That is not my bedtime reading. I also work on databases.
Also not for
or at least I
bedtime.
pretend to.
Yeah, exactly. No, you're doing that way more than I do. I pretend. You actually do that.
So going back to the comparison code, this is us comparing row A and row B using a schema, and this is the table schema. This is a schema that you would expect to be kind of static, right? But again, with these two dynamic rows, we have dynamic columns that we want to compare. And the call we see taking a bunch of time is this Parquet sorting schema that gets a Parquet schema, which is a different type from the schema that we're calling the method on, to be able to actually use a Parquet comparison on the two rows. So if we dive into here, this code goes over the sorting columns. So these are the columns we actually care about in a sorting order. We also have columns we don't care about to sort by. For example, a value column that maybe specifies, for example, for a CPU profile, like how many times a certain stack trace was observed. So things like that, like that's kind of arbitrary. So sorting by that column would kind of not really make sense from like a general view on the database. But actually, maybe it could, but for us, it doesn't really make sense. But those are like what non-sorting columns are. And here, the idea is that we're basically creating a new Parquet schema from the group of dynamic columns. And I think if we see the call here, these dynamic columns were actually obtained by merging the two dynamic column sets. So as I was talking about before, we could have like two profiles. One was a cockroach profile, another one was like some random program, but then the cockroach profile only has a cockroach label, and the other random program has a Linux kernel version. And so merging these two means you get both cockroach and Linux kernel version, and then you go over the rows and you say, oh, this one doesn't have a label for Linux kernel, let's put a null in there. So then you can compare them. So basically, given these merged dynamic columns, our output from this function is a Parquet schema. I'm just going to hide this thing a bit more. We create the Parquet schema by iterating over the sorting columns, creating the names. This is the dynamic name, and then create a new schema with this G, which is a group. It's basically like a schema defined in a tree structure, because you can have like nested schemas in Parquet. So that's why this code looks a bit complex, but that's basically what it's doing. So when I'm looking at this code, I think the first thing that I think is that, like, what is this code trying to do? It's basically returning, given a dynamic column set, a schema, which to me seems like it's just like a mapping, right? So if we get dynamic columns, return the schema, and like the big problem is obviously the allocation of this schema, because new schema, getting all these column mappings, like maybe not the actual allocation in terms of memory, but like creating this schema takes a bunch of time. Just like going over all the columns, deconstruction functions, and reconstruction functions. I don't really know what those are. I assume it has something to do with like when you're inserting values into columns, kind of define how you serialize them or whatever. But in the general thing is, it seems like this is a lot of code that we want to avoid.
Yeah.
And so intuitively, also one thing is that we have dynamic columns mapping from, but the mapping from dynamic columns to a schema. And I think a key insight here is that we have rows that might have different dynamic columns, but as a workload, in like in a very general sense, like you probably have like you probably reach a point where you have a very well-defined set of labels. So if we go back maybe to cloud, go to CPU samples again, we can see that every time series here has like a bunch of label sets, but most likely, like, you have samples that in this time series, the label set is all the same. Mm-hmm. So once, like, I guess what I'm trying to say is that maybe the word here is like the label set entropy is not very high, right? The label sets usually stay the same at a certain point. And
yeah, in Prometheus, we actually call this churn of labels or of series. So if we have, like, over time, if there are no deployments, no changes in the underlying infrastructure or anything, really, you have very little churn. So like all the workloads stay pretty much the same. And even like rewriting the time series database of Prometheus for Prometheus version 2 a couple of years ago, the maintainers, and I think like mostly Fabian Reinhardt, he looked at how can we deal with so much churn in these dynamic environments that Prometheus is going to run on in the future, aka Kubernetes, for the most part. He kind of also came up with this like LSM tree, and using the fact that like over time the churn is going to be somewhat more stable. So kind of like taking this property into account. And yeah, again, I just want to add that Prometheus calls this churn of time series. And we kind of have the same thing here, right? If we have little churn, over time, we can see that most likely the label churn is going to stay rather constant, at least, right? Mm-hmm. So that's a property we can also take into account in FrostDB.
Exactly. So, because if we don't see new labels that much, then it probably makes sense to cache this mapping of dynamic columns to the schema, because if the input doesn't change, the function output should stay the same.
Yeah.
So I think that's something we could try. So let's go ahead. Let's see. Okay. So
did we run the benchmark yet, like to get some numbers on?
I can run it. Yeah. Let's see.
Well, let's back and forth for.
I'm gonna add the changes to schema test. And then what I'll do is stash it, run the benchmark, which is called, oh wait, that's gonna break, right? Wait, let's just go to main branch. We can benchmark insert simple, I think it's called, in the main.
You want to change the file we write to at the end?
Yes. Call this bench main.
Or bench insert, because you already had the bench
Yeah.
main for the other one, right?
Bench insert main. Very specific. Okay.
That looks good. All right, nice.
So this translates to many, many nanoseconds. This is one problem. Like I wish they put commas in the output, but it's less comparable.
I guess you can use bench stat already on just a single file, and you get it like
much better output,
more nicely formatted. Yeah.
Yeah.
There you go. So 130 milliseconds.
Milliseconds, yeah. Cool. Yeah. So let's go back here. Pop our changes, which were the path changes. And now let's try to do this schema mapping thing. So getting a bunch of dynamic columns and returning a schema. So here actually there's an interesting thing that we already have like a sync map from, because this is actually something we already do with writers. So given a certain schema, when you're writing rows to Parquet files, you need a Parquet writer. And I think that over time we also saw that this Parquet writer was taking a bunch of CPU time, so we decided to pool it using a sync pool. But as we saw before, we actually have a map on top of the sync pool. So if you go writers, you see it's a sync map. And what this does is basically exactly what we need. So we can kind of like reuse parts of this code. We serialize the dynamic columns into a string to be able to get a key for those dynamic columns, look into the map, load or store the sync pool for that key, or insert a new sync pool. Then you need to get it, because it's just any type, not an undefined type. Then if that pool, if the pooled writer is nil, so here you would get the pool, like the writer pool. So this pool that would return writers, and if no writer is in that pool, like they're either all being used or none have been initialized yet, this is where you actually create the new writer. So in our case, it would be the new schema, and you return a pooled writer with that writer, and then a reference to the pool. And I think this reference to the pool basically exists so that when you put it, you can just like put it back into the given pool without having to pay the cost to reserialize those dynamic columns, as we saw here. So that sounds good.
A bit of finagling.
Yeah.
To use that word. But it's a bit back and forth, but definitely it's worth doing, right?
Yeah.
And we have so much of this going on.
Yeah. I mean, I think probably it doesn't, I don't know, like it's kind of, again, like a question of relative cost. I'm sure that serializing dynamic columns is expensive because, as you see, it's like a map from string to a slice of strings. So there's probably like a lot of map accesses there that need to happen. But I think the relative cost to creating a new schema is probably low enough that we don't need to do it, but like we might as well just do the same thing that we do above. So
at least the get writer didn't show up anywhere in the profiles, right? And that's kind of the thing. Like we have the data to show, oh yeah, this is like something worth thinking about, or it's actually it doesn't really matter. Like theoretically, looking at the code, we might think it makes sense to optimize up front, but yeah, I guess like the thing I'm getting is is that we can avoid like premature optimizations, and we can just write the code and then later on see, exactly, that's the thing we need to focus on, and it's completely a different thing that we anticipated it's going to be, right?
Yeah.
I mean, there are always like easy wins that you can do when writing code, just like pre-allocating, I don't know, a slice, because you know upfront the amount of elements you're going to put into, because you're like writing from one slice to another and transforming it, so you can know the amount of elements you would put into the new slice. Things like that I think make sense, but otherwise, like at this point, I'd rather have some data on it and then improve it later on.
Yeah, I mean, it's a good point. I think continuous profiling is definitely also useful to see like what doesn't show up. Because a lot of times I think as engineers we're like, oh yes, this must be the answer. This must be why everything is slow. But then, the actual data might show that it's not called that much. So it's not really such a hot path as we expected it to be.
Yeah, exactly. Like if you were calling this thing like 99% of the time of the software that it's when it's running, yeah, okay, this might be worth like improving, right? But it's just called every now and then, so who cares?
Yeah, exactly. So let's write this. So tab 9 is giving me some pretty good suggestions. So I'll just press tab.
And get errors, but good enough.
This is not correct, but
I guess in that sense, Copilot is actually super similar, because that also happens a bunch with Copilot.
The good thing is that we see that there's this sorting schemas field that I need to add, which should be a map from the dynamic columns to pools, and here basically do the same thing. And here, this is where we should be actually calling, what is it, s dot new, actually no, is Parquet sorting schema. This is the function that we're calling every time, but now we only want to call if we need to create a new schema. So we can just shout out to that function and then not use a new keyword, call it PS. Oh, and then we also need to create a new struct that holds the pool that we want to return it to, plus the actual object. So let's call this a pooled, maybe it's a bit too long, but better be descriptive. And then
fine to me.
Yeah. So a pool, and then I guess we can call this just the schema. Let's see, pulled Parquet schema, delete this, apart from the error, oops, with a, this was it, right?
Yeah, I think something's not happy.
It's the return type.
Oh yeah. Pool schema. Yeah.
So that should be the return type, pulled Parquet schema, error. And then we don't need to read, this is a writer specific thing, because this is, okay, so basically, obviously if we don't get into this if statement, then we have a pooled schema that we just want to return. So we would just return the pooled object cast to a pulled Parquet schema. Okay. And then the next thing we need to write is put, thank you, tab 9. Put Parquet sorting schema. Just have to forgot to put schema at the end. So we would just, what is it, ps dot pool dot put. I think this should be it, right? Let's see the put writer. Yeah, it just puts it into the pool. And we don't need to do anything like reset the writer as the put writer function does here, because the schema is static. Like we're not doing any state changes to it or anything. We just need it to represent a certain structure of those dynamic columns to store rows. So the nice thing is that if we see rows that have the same label set of rows we've seen before, we'll just reuse the schema instead of calling new schema.
And that is determined by the key we create for that schema, right?
By the key, yeah. By the key,
Okay.
basically this is a serialized dynamic columns. So the columns that can change in a row, we'll just take all the column names and say like, these are the variable columns. Do we have a schema for this set of columns? If the answer is yes, then that would return the schema. And by the way, it's not the columns of just one row, it's the columns of the merged rows. So
right.
The first step is to merge the variable columns, the dynamic columns of both rows, and then use that as a key to get the parquet schema.
So we're kind of like looking at pooling the union of schemas, which is probably a lot higher to occur. Like the probability of that occurring is a lot higher than the individual schemas that might just be for one specific
correct
process or whatever. Yeah, nice.
And the nice thing is that like I think the serialization, if we look at it, because you're probably wondering like, oh, we might have like arbitrary rows with columns in like arbitrary orders as well. But I think part of serialized dynamic columns is a sort. So you basically get like, for a given set, you always get the same key. And this is probably also like a bit of an expensive code. I'm sure like it probably shows up on profiles, but always corroborate that with data. But yeah, this is something that actually we did see on the profiles. We saw it in the merged dynamic columns. I don't want to jump around too much, but let's see. Where was it? No, I can't find it. That was somewhere. Whatever.
Maybe use the filter by function thing. But yeah.
MNS. No, didn't find it.
That's an error saying there's nothing with that name. No very descriptive error, I guess.
Yeah. But I guess we can go back to the coding. So we created this function to get the parquet's pooled schema, then put it back. So now what we need to do is change the call side, which is the actual comparison. And instead of calling parquet sorting schema, we'll get a pooled schema, but this should be get parquet sorting schema according to these dynamic columns. What does this return? Just an error? Oh, it actually panics. I guess the code shouldn't panic, but at the same time, this is a comparison function, so it'd be very annoying to have to handle an error every time we call it. Trade-offs. So this, in the pooled schema, we would get the internal schema, and then we got to remember to put it back. Otherwise, it will just be allocated. We'll just not have changed anything. So we put the pooled schema back. And I think that should be it. We've got the profiles back, meanwhile. Okay, should we run the benchmark?
I guess, yeah. Let's see what it changes.
Okay.
How much we're gaining.
Benchmark insert simple. Benchmark insert
stream. Schema.
Stream. Oops. Map.go. Okay. Schema.go 1094. So this is the problem because we're not actually initializing the map. So let's go to, because I don't actually think it needs to be a pointer to a map. We would probably just use a map value. Oh, Nicholas is dropping.
Yeah.
Thank you very much for stopping by.
Yeah, thanks for hanging out and commenting. Curious to still see one of your streams on Argo CD. So definitely let us know on Twitter or somewhere, and we'll take a look. And maybe we can, as I said earlier, maybe we can like profile Argo CD in the future. I'm pretty sure we can find some things here. So we should be able to find something in Argo CD as well. There's always some low-hanging fruit.
Oh yeah.
But yeah, take care and have a great weekend.
Cool. So the panic was that it was nil. So I think that should work now.
It's not panicking.
It's not panicking. And it seems to be, what is it, bench, insert, main?
Yeah.
Seems to be faster.
It's from like...
This is the moment of truth. Bench stat, insert main versus insert stream. Nice. So we see that on our insert benchmark, we've improved this by 50%. And this also includes the dynamic column changes we did at the beginning of the stream to not allocate when getting the name. So the summary is that we've improved the time of these operations, so the insert operations, by around 52%. We have also reduced allocations by 67%. And this is the space allocated, and these are actual number of allocations. So you could have like very few but large allocations, or many but very small allocations. And it's sometimes actually worse to have many but very small allocations because of the GC that we were talking about before.
Yeah, and I think that's a good thing to point out again, right? The reason, or like the CPU time that we're seeing above is just for the direct like function call we're doing, but we also probably turned down the GC CPU time quite a lot as well, that we were seeing at the profiles on the right hand side earlier, given that we are allocating a lot less. So we are indirectly gaining even more CPU time back as well.
Yeah,
that's
exactly.
Pretty wild though. Just using the schema and in a pooled fashion.
Yeah, it's actually, so I've seen like sync.pools are useful in cases like this, and the reason we're using a sync.pool, by the way, is because, and why not just like a normal map? Well, it's because we're doing a bunch of possibly concurrent inserts right against a database, so we can't just use a map that doesn't have protection for concurrent accesses, and that's basically why we use sync.pool. But in a lot of cases, like you might put a sync.pool in your code to like pull allocations, but you might see that actually the performance decreases. Well, the performance gets worse because there's a certain overhead associated with a sync.pool because you're introducing all these concurrency protections in your code that sometimes make performance worse. So it really depends on the specific use case of when you put sync.pool in your code. I've seen it a lot of times when, it's sort of like intuitively made sense to put sync.pool in the code to pool allocations, but then actually the performance got worse, and you're like, oh, well, that's a shame. But in this case, it seems to help a lot because we have like a ton of allocations concurrent as well. So, the overhead we're paying as well for using a sync.pool is probably worth it, just to pull allocations across different Go routines. So, yeah. So, I mean, the nice thing is that all these changes that we did resulted in a 50% improvement of the insert call, right? So, if we go to benchmark insert simple, well, there you go. We're actually measuring in these benchmarks is getting a table and calling insert on the table. So basically the call that we're seeing here, right? So calling this basically says,
you need to reload. Sadly, that's a thing sometimes. Ah, there you go.
But the what I'm trying to get at is that we're benchmarking this specific insert goal. So we've improved this by 50%, which is what our benchmark says. And it's also like a very relatively simple benchmark. So our more complex ones, I'd be kind of interested in seeing what the change is. But we've out of 65%, we've improved around 50%. So that's like a 30+ percentage improvement on the highest use of CPU in our cluster over the last 15 minutes, which is pretty significant with these two like little changes.
Oh yes.
So,
and it's like continuous load, right? I think that's also a really good one to point out. It's not like we get constant queries. We don't, but we do get constant writes where like Parka agents over time, just like they're also writing over time constantly into Parka. Every 10 seconds we get a write, and if we can cut down 30% there, that's quite an achievement for sure.
Yeah. So I'll call this success.
Yeah.
So that's pretty cool. So we got rid of this new schema call. So this is where I was seeing it, merge dynamic columns. Right, so these merge strings, we see the sort taking up some time, and this is basically like the key creation that we're doing. Merge strings also pulls sort strings to create a single string with all the column names merged.
It's good to see though that this is only like 1% or something. So like paying the price for generating the key is still totally fine, but now we can use it in a sync pool, and cut down so much CPU time by reusing the schemas there.
Absolutely.
Yeah. Nice. Yeah, I mean, fantastic. Anything else you wanted to get into? I think that was like the gist of it, right?
Yeah, I think, I mean, especially all this stuff is comparisons. We increased this merge dynamic columns, I guess it's like 2%, so it's pretty small. We improved this, the path in ascending. So yeah, I mean, I think these are pretty good improvements for today.
Very cool. Yeah, I think we don't want to deploy this right now. We can probably follow up with like a flame graph screenshot of some sorts in the next.
Yeah.
We have merged this and it's been running for a bit, and we can see. Maybe it's worth taking a screenshot right now, or like actually not taking a screenshot. Let's actually just pull a pprof profile and put it onto pprof.me. So if you go to,
because I can't do a merge profile, right? So if I just
no, it should take exactly what you have there, and if you go to the left one, the share button, you can say like the pprof, the 50-minute CPU for the stream or something. Nice, and then we can put this in chat or something, but I think that is kind of what we can use in the next days, to then take another of these 15-minute CPU profiles, and we can then probably just do a diff on both of them.
Oh yeah, that sounds good.
See the impact, right? Okay, so I dropped the thing in the chat if you want to take a look at the flame graph yourself that Alfonso just created, but we can use that to compare it against another one in a couple of days. Sadly, it's too much. Like we thought of like deploying this right now. Maybe at some point in the stream we'll be able to also deploy the changes and see a drop. I think that would be the ideal scenario. like see it happening. But I think the reality for most teams is that CI needs to run for a bit, and then you just sit on the stream. So we'll keep you
Talking
posted.
about things.
Also, Friday,
exactly.
Friday deployments.
Friday afternoon, 5:30 p.m. The best time to deploy.
Fine for us. Fine for us. That wouldn't be too bad. But
this is how I like to spend my Friday afternoons, just deploying to prod.
I'm happy with that, but I doubt anyone wants to watch our CI and more boringly watch us while we watch CI, because you probably won't see it. So
I also will probably clean up the PR and stuff like that. But I can clean it up, put up the PR. We can maybe tweet about it so people can follow up, see the changes on GitHub.
Yeah,
because it's open source again, and then we can follow up either on the PR or on Twitter, or maybe even next stream on how the
do a quick
improvements.
Quick recap from the previous stream, but we're gonna share it on twitter.com/polarsignals.io. So give us a follow there so you can see the stream kind of follow-ups. Sounds good to me. Anything else you wanna show on the stream? I think.
No, I think that's it. Our goal is to profile FrostDB and get some significant improvements, and I think we managed to do that. For what mathematically is like a 35% improvement of CPU usage in the last 15 minutes. And again, it was like a component that was taking up a lot of time, right? So I guess I'm not sharing my screen anymore, but the highest line we saw in the time series, this spike is probably like compaction or something like that. But we see in the labels that the highest CPU usage in our cluster are these storage nodes. So reducing 30% of CPU time on something that's pretty significant, I think is it's a win, definitely.
I think we can leave it at that. And there's also going to be a win for all the Parker instances, as we said at the beginning. Like this is also going to improve things for the community, right? Like we're definitely going to put that upstream in Parker as well. I think there's like the meta store is sadly a bigger denominator of overall CPU time, but still you gain some cycles and some percentage of Parker installations as well. Really cool. It was good like watching you go through the flame graph, and I don't know if I wonder how similar it is to the way I approach it, or others like Frederick or Kemal or anyone really at Polar Signals approaches looking at flame graphs. But I think it was good like learning from the way you approach things there as well.
Do you think it's different than the way you do it?
Not really. I think I'm actually used to using the filter by function a lot more these days. So I might just like look at some things in the big scheme of the overall infrastructure, but then I like.
So what you're looking for. You just want to see like how much it actually takes.
Exactly, and then I might just like search for that thing, and all of a sudden like see the instances of only the stack traces that contains the string I'm looking for. But I think definitely a good approach as we've seen.
Definitely. This was fun.
We'll be back, and the two of us will be back probably as well with another stream. We have already some things lined up, so that will be super fun. More guests, maybe next week, I don't know, or the week after, but we'll see. And I'm pretty sure Frederick is going to do another stream with guests as well. So there's definitely more Let's Profile happening in the next weeks and months.
So many guests.
Maybe bring the guests on the stream. I think that would be really cool, like profiling other open source software, right?
Maybe we'll have Nicholas with Algo CD.
I don't know if he still watches the recording in the end, but I hope I was like clear enough that profiling Argo CD would be super interesting to us as well, because I'm pretty sure it's deployed on a lot of clusters.
Yeah, absolutely. I mean, looking, because this was also a profile, like profiling our own production environment, but so something that's like very nice is as Matthias says, profiling code that runs in a lot of clusters around the world, where even like we got a 30% CPU improvement on our own cluster, but if you do like 1 or 2% on something that a ton of people use across the world, then that's like very, very significant.
Yeah, I think we had this with Containerd, for example, a previous stream, right? Yeah, so bring the open source software in and let us know if you're watching, if you want to like have something that you want to profile with us.
Yeah, exactly. If there are any suggestions, I think that'd be pretty awesome.
Okay, I think we can wrap it up there. Again, follow us on Twitter and YouTube for more of the list profile streams, and we'll follow up on Twitter with the pull requests, and then in the next days with a comparison on how much CPU we actually saved, not theoretically that we just like back on the envelope math.
It was 100%, I swear.
Yeah. But what we'll actually see in production. Okay, thank you for joining, Alfonso. Actually, thank you for having me on your
hosting, Matthias.
Thank you for having me on your stream. I was just like tagging along.
This is your stream. You're the one controlling all the buttons.
Okay, fair enough.
You could like remove me right now if you wanted to.
Yeah, I can, but I'd rather not. I was great having you on the stream.
Well, it's great being here.
See you. All right. Take care, Michael. And yeah, see everybody the next time. Take care. Have a great weekend. And everyone watching the recording, I hope you rest from KubeCon. All right. Take care, everybody. Bye-bye.
Bye-bye.